There is a place in the universe where the rules we take for granted no longer apply, where gravity doesn't just pull, it consumes, where space and time twist into knots, and light itself is swallowed into an abyss from which there is no return. This is the realm of total gravitational collapse, one of the most extreme and mysterious processes the cosmos has to offer. It's where stars meet their end, where matter is compressed beyond imagination, and where the fabric of reality is stretched to its absolute limit. And in these moments of ultimate transformation, phenomena occur that defy belief and deepen our awe of the universe. In this video, we're going to explore 20 breathtaking events that happen only during total gravitational collapse, from the formation of event horizons that cloak regions of space-time, to the emission of Hawking radiation that blurs the line between quantum mechanics and gravity. We'll witness how matter is stretched into strands, how light is bent into glowing rings, and how gravitational waves ripple across the cosmos, carrying secrets of some of the most violent events since the Big Bang. Each of these phenomena opens a window not only into how stars die, but how the universe itself operates under conditions so extreme they challenge the very foundations of physics. You are about to embark on a journey to the edge of understanding, a voyage into the heart of darkness and light, where destruction and creation are two sides of the same coin. By the end, you'll have glimpsed realities that few have ever pondered, and you'll see why these rare moments of collapse are not endings, but revelations. So join us as we uncover the hidden wonders that occur when gravity wins, and the cosmos shows us just how astonishing it can truly be. At the heart of every black hole lies one of the most profound predictions of Einstein's theory of general relativity, the space-time singularity. This is the ultimate endpoint of total gravitational collapse, where all the mass of a once giant star is crushed into a point of infinite density and zero volume. The laws of physics as we know them simply cease to function here. Concepts like space and time break down entirely, and our equations yield nonsensical answers involving infinities. It's a place where the familiar rules of the universe hit a wall, signaling that we need a deeper theory, perhaps one that successfully merges gravity with quantum mechanics, to truly understand what happens. This singularity is always hidden from our view, shrouded safely within the event horizon of a black hole, a concept so crucial it's enshrined in the cosmic censorship hypothesis. But its influence is felt everywhere. Its immense gravitational pull dictates the motion of stars and shapes the accretion disks of superheated gas that whirl around it. Theoreticians like Roger Penrose used powerful mathematics in his singularity theorems to show that these points of infinite curvature aren't just mathematical oddities, they are inevitable under the extreme conditions of gravitational collapse. Contemplating the singularity forces us to confront the limits of human knowledge. It represents a frontier where our current understanding ends and the next great revolution in physics must begin. What truly occurs at the center? Could quantum effects prevent this infinite collapse, leading to a quantum bounce or something entirely unexpected? The singularity is not merely a destructive end but a generative puzzle, pushing the boundaries of cosmology and challenging us to look beyond Einstein's magnificent theory to something even more fundamental. But what exactly is this event horizon, and how does it come to be? Picture a dying star, once brilliant and massive, now collapsing under its own immense weight. As it shrinks, its gravitational pull grows so intense that at a certain distance from its center, the escape velocity exceeds the speed of light. This critical boundary, this point of no return, is the event horizon. It's not a solid surface you could touch or see. It's a one-way gate in the fabric of spacetime itself. From our perspective outside, anything that crosses this threshold, a spacecraft, a particle of light, an entire star, seems to freeze in time, fading from view as its light red shifts into nothingness. Yet, for the unfortunate object itself, the crossing would be uneventful, a silent passage into a realm from which there is no comeback. The formation of an event horizon is a direct consequence of Einstein's theory of general relativity, which describes gravity not as a force but as a curvature of spacetime caused by mass. The more mass is compressed into a smaller volume, the deeper the gravitational well it creates, warping spacetime until it literally folds over on itself. Think of it like a river flowing towards a waterfall. The event horizon is the edge of that waterfall. Well before you reach it, you can still swim back to safety. But once you pass the brink, the current becomes irresistible, pulling you inevitably downward. This is why the event horizon is often called the point of no return. It's the brink of the cosmic waterfall from which not even light can climb back out. This has profound implications for our understanding of the universe. For one, it acts as the ultimate cosmic veil, permanently separating the interior of a black hole from the rest of reality. Whatever happens inside is hidden from external observers, creating what physicists call an information paradox. If we throw a book into a black hole, is the information in that book lost forever, violating quantum mechanics? Or is it somehow preserved on the event horizon itself? This isn't just a philosophical puzzle. It strikes at the heart of whether the universe is fundamentally predictable. The event horizon, this invisible mathematical surface, challenges the very nature of causality and what we can ultimately know about the cosmos. Observationally, the event horizon is the defining feature that makes a black hole truly black. It's the reason we can't see the singularity at the center, but we can see its shadow. The groundbreaking image released by the Event Horizon Telescope collaboration in 2019, a fiery ring of light surrounding a dark void, wasn't a picture of the event horizon itself, but of the photon sphere and the light warping around it, outlining the shadow cast by the horizon. This monumental achievement provided the strongest direct evidence yet for the existence of these enigmatic boundaries, confirming predictions made by relativity a century ago and opening a new window into studying gravity in its most extreme form. Now, at the very heart of this collapse, something even more bizarre and counterintuitive occurs. Deep within the protective shroud of the event horizon, all the matter that was once a star is compressed into a single point of infinite density. This is the space-time singularity, a concept so extreme that it represents the ultimate breakdown of our physical laws. Imagine taking the entire mass of our Sun, which is over 1 million times the volume of Earth, and crushing it down into an area smaller than a single atom. Then continue crushing it infinitely further until it occupies precisely 0 volume. That is the essence of a singularity, a place where the familiar concepts of space and time cease to have any meaning, and the mathematics we use to describe the universe simply stop working, yielding impossible answers like infinite curvature and infinite energy density. This isn't just a theoretical oddity. The work of physicists like Roger Penrose has proven through his singularity theorems that under the extreme conditions of total gravitational collapse, the formation of such a point is inevitable according to the rules of general relativity. It is the inescapable destiny for a sufficiently massive collapsing star, yet this creates a profound problem for science. A singularity is a signal that our current understanding of physics is incomplete. General relativity, which so beautifully describes gravity on large scales, cannot handle these quantum scale infinities. It's like a calculator being asked to divide by zero. The rules themselves break down. Because the singularity is always hidden from our view by the event horizon, we are protected from its chaotic and lawless influence. From the outside, the black hole behaves in a predictable, orderly manner, defined only by its mass, spin, and charge. But on the inside, the singularity dictates the fate of anything that crosses the horizon, ultimately destroying it. This cosmic censorship, as it's called, may be nature's way of preserving order in the universe, ensuring that the unpredictable insanity of the singularity remains locked away, unable to affect the rest of reality. This fundamental paradox forces physicists to search for a deeper theory, one that can marry the vast scale of gravity with the tiny quantum world. We need a theory of quantum gravity to tell us what truly happens at the center of a black hole. Does matter actually reach infinite density, or do unknown quantum effects create a repulsive force that halts the collapse, perhaps forming something exotic like a Planck star or a knot of superstrings? The singularity is not an end to the story, but a giant question mark, pointing the way toward the next great revolution in our understanding of the cosmos. Now, let's step into one of the most mind-bending consequences of this collapse, a distortion so profound it affects time itself. As a star collapses into a black hole, its immense gravity doesn't just warp space, it stretches and slows time in a phenomenon known as gravitational time dilation. This isn't science fiction, it's a direct prediction of Einstein's general relativity, stating that time passes slower the closer you are to a powerful gravitational source. Near the event horizon of a forming black hole, this effect becomes so extreme that from the perspective of a distant observer, time appears to grind to a complete halt. To grasp this, imagine a clock falling toward the event horizon. We, watching from a safe distance with a powerful telescope, would see that clock tick slower and slower. Its hands would move in ever-decreasing increments, its light would redden and dim, and as it approached the point of no return, it would seem to freeze entirely, never quite crossing the threshold from our point of view. Yet, for an astronaut riding on that clock, their personal experience would be entirely different. Their watch would tick normally, and they would cross the event horizon without any sudden jolt or dramatic sensation, all within a finite amount of their own time. This creates a bizarre cosmic paradox. The same event, the crossing of the horizon, happens in a finite time for one observer and takes an infinite amount of time for another. We actually have everyday proof that this strange effect is real, right here on Earth. The ultra-precise atomic clocks on GPS satellites in orbit, experiencing slightly weaker gravity than we do on the planet's surface, actually run faster by a tiny, measurable amount. If engineers didn't constantly correct for this relativistic time drift, the entire GPS system would become inaccurate by several miles within just a single day. This confirms that gravity's influence on time is a fundamental feature of our universe, but near a collapsing star, the effect isn't measured in microseconds. It's magnified to an almost incomprehensible degree. This radical distortion forces us to confront questions about the nature of reality and causality. If we see a star collapsing into a black hole, and from our frame of reference that collapse appears to take forever, does that mean black holes never truly finish forming? In a sense, from our distant vantage point in the universe, every black hole is forever frozen in the act of its own birth, a perpetual monument to its final moment of collapse. This has profound implications for how we interpret astrophysical events and what we can truly know about the universe's most violent transformations, blurring the line between a finished object and an eternal process. But the story of total gravitational collapse isn't just about things falling in. It's also about something astonishing leaking out. In the chaotic final moments as an event horizon forms, a subtle quantum process begins that slowly steals energy from the collapsing object itself. This is Hawking radiation, a phenomenon that forever changed our understanding of black holes and revealed a deep, invisible connection between the vast force of gravity and the tiny, probabilistic world of quantum mechanics. To understand how this works, we need to peer into the seething nature of empty space. According to quantum theory, the vacuum isn't truly empty. It's a bubbling sea of virtual particles, pairs of particles and antiparticles that constantly pop into existence and then annihilate each other almost instantly. Normally, this happens without any net effect. But when this quantum fluctuation occurs right at the precipice of a newly forming event horizon, the extreme gravity violently rips these particle pairs apart before they can destroy each other. One particle gets captured by the immense gravitational pull and falls inward, while its partner is ejected outward, escaping into the universe as real, detectable radiation. This process, first calculated by Stephen Hawking in 1974, has a profound consequence. It causes the collapsing object to lose mass. The energy to create the escaping particle has to come from somewhere, and it's drawn directly from the gravitational energy of the collapse itself. So, contrary to the classical idea of a black hole as a one-way street that only grows, Hawking radiation means these objects can actually shrink, very slowly evaporating over astronomical timescales. For a stellar mass black hole, this process would take longer than the current age of the universe, but for a much smaller, theoretical primordial black hole, this evaporation could culminate in a final, explosive flash of energy. This discovery was revolutionary because it forced the two great pillars of modern physics, general relativity and quantum mechanics, to finally speak to each other. Hawking radiation is a purely quantum effect that occurs in the most extreme gravitational field imaginable. It tells us that gravity and quantum phenomena are not separate. They are intertwined in the fabric of space-time, especially at its most strained and broken points. This radiation provides our first and best theoretical glimpse into what a theory of quantum gravity might look like, offering clues from the edge of a black hole. Perhaps its most staggering implication is what it did to the concept of the information paradox. If a black hole evaporates completely through Hawking radiation, what happens to all the information about the matter that fell in? Quantum mechanics insists that information cannot be destroyed, yet the radiation Hawking first described was purely thermal, carrying no specific information about what made up the black hole. This suggested a fundamental contradiction, a violation of quantum law that physicists have been wrestling with for decades. Modern theories, like the idea of holographic storage of information on the event horizon, are direct attempts to resolve this paradox that Hawking's brilliant discovery so elegantly exposed. While the stretching of time and the subtle glow of quantum radiation are phenomena that challenge our perception, the sheer physical violence of gravitational collapse presents a spectacle that is almost easier to visualize and far more visceral. This brings us to one of the most dramatically named processes in all of astrophysics, spaghettification. Imagine not just falling into a black hole, but being pulled and stretched like a piece of soft taffy, elongated into a strand of atomic pasta long before you ever reach the central singularity. This isn't a fate reserved for hypothetical astronauts. It's the inevitable end for any chunk of matter, be it a gas cloud, a planet, or even an entire star, that ventures too close to a sufficiently dense collapsing object. The cause of this bizarre transformation is a difference in force, a concept we're actually familiar with here on Earth, just on a much gentler scale. Our moon exerts a gravitational pull on our planet. This pull is slightly stronger on the side of Earth facing the moon and slightly weaker on the far side. This difference, however small, is what stretches the oceans, creating the daily rise and fall of the tides. Now, amplify that effect by a factor of billions. Near a black hole, the gravitational pull on your feet, if you were falling in feet first, would be catastrophically stronger than the pull on your head. Your body wouldn't just feel a gentle tug, it would be subjected to an unimaginable stretching force, pulling you apart longitudinally while simultaneously compressing you from the sides. The result is a one-way trip to becoming a stream of subatomic particles, stretched infinitely thin in the direction of the collapse. This extreme tidal force isn't just a theoretical horror story. It has a very practical and observable impact on how black holes consume matter and grow. Most stellar mass black holes are part of binary systems, orbiting a companion star. They slowly siphon gas from their partner, which doesn't fall in directly but spirals into a flattened, superheated structure known as an accretion disk. The inner edge of this disk is defined by the point where tidal forces finally overcome the internal forces holding the matter together. This is the spaghettification zone. Here, clumps of gas and dust are not just heated by friction, they are violently shredded, their structure obliterated, and their component atoms aligned into long, thin streams that then spiral inward. This process liberates a tremendous amount of energy, contributing significantly to the intense X-ray emissions that our telescopes detect from these binary systems. The scale of this destruction is almost beyond comprehension. Consider a star that wanders too close to the supermassive black hole at the center of its galaxy. The star will be torn apart not by impact, but by tidal forces in what astronomers call a tidal disruption event. The side of the star closer to the black hole is pulled in so much more forcefully than the far side that the entire celestial body is ripped apart in a single, catastrophic pass. The resulting debris is spaghettified, stretched into a long, thin arc of stellar material that then rains down onto the accretion disk, creating a brilliant flare of light that can outshine the entire galaxy for a brief period. This terrifyingly beautiful event gives astronomers a direct window into the feeding habits of these cosmic monsters and allows them to measure the properties of black holes that would otherwise remain hidden in darkness. Ultimately, spaghettification is a stark reminder that gravity is not a uniform force but a gradient, and in the most extreme environments of the universe, that gradient becomes a weapon of cosmic demolition. It transforms complex structures into their most basic, linear form, feeding the insatiable appetite of the singularity. This violent process, acting at the precipice of the event horizon, is a key driver behind some of the most energetic and luminous phenomena we observe in the cosmos, turning the final moments of infalling matter into a brilliant and destructive display of pure gravitational power. Just beyond the point of no return, where gravity's pull becomes absolute, lies a region of pure light and shadow, a place where photons themselves become trapped in a dizzying cosmic dance. This is the photon sphere, a breathtaking phenomenon that forms during gravitational collapse, creating a shell of orbiting light around the newborn black hole. Imagine a place where the fabric of spacetime is curved so tightly that light, which always travels in straight lines, is forced into a perfect circular path. Photons streak around this sphere at the speed of light, not falling in and not flying away, but trapped in an unstable orbit, like a satellite perpetually circling the Earth without ever slowing down. This sphere marks the last possible stable orbit for light, a final frontier between the observable universe and the absolute darkness within. The visual consequences of this are nothing short of spectacular. Because light can loop around the photon sphere multiple times before either escaping to an outside observer or finally spiraling inward, it creates incredible optical illusions. A single star sitting directly behind a black hole from our viewpoint could appear not just once, but as multiple images, distorted into a brilliant ring of light encircling the black hole's shadow. This is known as an Einstein ring, a direct prediction of general relativity made a century ago that we can now observe with powerful telescopes. It's as if the black hole becomes a monstrous gravitational lens, bending the very fabric of reality to show us copies of the cosmic landscape behind it, all wrapped around a central point of infinite darkness. The groundbreaking image of the supermassive black hole at the heart of the galaxy M87, captured by the Event Horizon Telescope, provided our first breathtaking glimpse of this effect in action. That now iconic image of a fiery ring of light surrounding a dark void, that ring is intimately connected to the photon sphere. It is the light from the superheated accretion disk, bent and lensed by the immense gravity, outlining the shadow cast by the event horizon. By carefully studying the size, shape, and brightness of that ring, scientists can perform precise measurements of the black hole itself. The diameter of the photon sphere's shadow directly reveals the black hole's mass, a fundamental property that dictates its gravitational influence. But the revelations don't stop with mass. The precise shape of the shadow and the photon sphere can also tell us if the black hole is spinning. A rotating black hole, described by the Kerr solution to Einstein's equations, drags space-time around with it in an effect called frame dragging. This rotation squashes the photon sphere, making it slightly oblate rather than a perfect sphere. A stationary black hole would cast a perfectly circular shadow, but a spinning one will have a shadow that is flattened on one side. By analyzing the subtle distortions in the light ring, astronomers can therefore deduce the spin of the black hole, unlocking secrets about how it formed and how it has grown over billions of years by consuming matter and energy. This makes the photon sphere one of the most powerful natural laboratories in the universe for testing the limits of general relativity. It exists in an environment where gravity is so strong that Newton's laws completely fail, and only Einstein's theory can accurately predict the behavior of light and matter. Any deviation from what relativity predicts in the structure of the photon sphere could be a sign of new physics, perhaps hints of the long-sought theory of quantum gravity. It serves as a cosmic checkpoint, a natural experiment confirming that even under the most extreme conditions imaginable, the rules set out by Einstein over a century ago continue to hold sway, governing the motion of everything from planets to photons on the very edge of eternity. But the strange warping of spacetime around a collapsing object doesn't end at the photon sphere. If the dying star was rotating, and most stars do spin, its final collapse amplifies that rotation to an incredible degree, much like a figure skater pulling in their arms to spin faster. This rotation creates a bizarre and dynamic region around the black hole called the Ergosphere, an oval-shaped zone of twisted spacetime that lies outside and envelops the event horizon. Within this ergosphere, something truly mind-bending occurs. The fabric of space and time itself is dragged around by the black hole's rotation, a phenomenon known as frame dragging. It's as if the black hole is spinning in a pool of honey, and the very space-time around it is forced to swirl along in a relentless cosmic whirlpool. This effect means that within the ergosphere, it is utterly impossible to stand still. No force in the universe can keep an object stationary relative to the distant stars. Everything, every particle of dust, every photon of light, even time itself, is caught in this irresistible current and forced to move in the direction of the rotation. You could fire your rocket engines at maximum power trying to hover, but you would still be swept along, a helpless raft caught in a gravitational river. This isn't just a theoretical idea. We've actually measured a much milder version of frame dragging here in our own solar system. NASA's Gravity Probe B mission, after years of painstaking analysis, confirmed that the rotating Earth ever so slightly drags space-time around with it, just as Einstein's theory predicted. Around a newborn rotating black hole, this gentle tug becomes an inescapable, violent torrent. This churning of space-time isn't just a curiosity. It opens up the possibility of one of the most incredible energy generation mechanisms in the entire universe. Physicist Roger Penrose realized that this twisted region could be used as a cosmic power plant. In what's now called the Penrose process, an object could fly into the ergosphere and split into two pieces. One piece, carrying negative energy, is designed to fall past the event horizon, effectively slowing the black hole's spin ever so slightly. The other piece, now carrying more energy than the original whole object, gets flung back out into space. It's a seemingly magical trick where energy is not created, but extracted directly from the black hole's rotational momentum. This process effectively mines the energy stored in the spin of the collapsed object, turning the ergosphere into a powerhouse of unimaginable scale. The influence of this frame dragging extends far beyond theoretical energy extraction. It is a key architect of some of the most spectacular and violent phenomena we observe in the cosmos. The superheated accretion disks of matter swirling around black holes don't just spin in simple circles. Their inner regions are gripped and twisted by the dragging of space-time, creating immense magnetic fields that are wound up like cosmic springs. These magnetic fields can channel and accelerate some of the infalling matter, launching it away from the poles of the black hole at nearly the speed of light, forming colossal jets that can stretch for thousands of light years across galaxies. The incredible power and precision of these jets, seen erupting from quasars and microquasars, are directly fueled by the rotational energy of the black hole, an energy tapped through the frame-dragging effects within the ergosphere. This dynamic environment, where space-time itself is in motion, is what transforms a simple collapse into an engine of creation, shaping the evolution of galaxies and lighting up the universe with some of its most energetic displays. Now, as we've explored the warping of space-time around a collapse, it's time to consider how that warping can itself become a signal, a ripple that travels across the cosmos. When a massive star undergoes its final, violent collapse, or when two black holes spiral into each other, they don't just distort the space around them quietly. They actually shake the very fabric of the universe, sending out waves of distortion that travel at the speed of light in all directions. These are gravitational waves, and their detection has opened up an entirely new sense with which we can perceive the universe, allowing us to literally hear the echoes of these catastrophic events. For a century, gravitational waves were a purely theoretical prediction of Einstein's general relativity. The mathematics showed that any accelerating mass should produce these ripples, but they were thought to be so incredibly faint that detecting them would be nearly impossible. Einstein himself doubted we would ever have the technology to find them. The key to generating a strong, detectable signal is extreme acceleration in an incredibly asymmetric system. This is precisely what happens in the final moments of gravitational collapse or the merger of two dense objects like neutron stars or black holes. As these massive bodies whip around each other at a significant fraction of light speed before colliding, they create a chaotic storm in spacetime, pumping immense energy into these rippling waves. The quest to detect these waves culminated in a triumph of human ingenuity with the Laser Interferometer Gravitational Wave Observatory, or LIGO. In September 2015, after decades of development and refinement, LIGO twin detectors in Louisiana and Washington state registered a signal that would change astronomy forever. The signal was a mere wobble in the fabric of spacetime, a change in the length of LIGO 4-kilometer, long arms smaller than the width of a proton. But its pattern was unmistakable, a rapid rise in frequency and amplitude, a chirp that lasted a fraction of a second, caused by two black holes roughly 30 times the mass of our Sun spiraling into each other and merging over 1 billion light-years away. For the first time, we had direct observational proof that black holes exist, that they can merge, and that gravitational waves are real. That chirp is more than just a signal, it's a rich source of information. By analyzing the precise shape of the wave, how its frequency sweeps upward, and how it rings down after the merger, scientists can decode the story of the event that created it. The waves reveal the masses of the objects involved, their spins, and even the orientation of their spin axis relative to their orbit. It's like listening to a drum and being able to calculate not only the size of the drum, but also the material it's made from and how it was struck. This allows us to study the properties of black holes and neutron stars in a way that is completely independent of the light they emit, giving us a pure, direct view of gravity in action. This new field of gravitational wave astronomy is like giving the universe a voice. Before 2015, our view of the cosmos was entirely based on light, from radio waves to gamma rays. But many of the most violent events, like the collision of two black holes, are completely dark. They don't emit any electromagnetic radiation at all. Gravitational waves are our only way to see them. They complement traditional astronomy, revealing a hidden population of dark objects and cataclysms that were entirely invisible to us before. Every new detection adds another data point, helping us build a census of black holes and neutron stars throughout the universe and understand how these binary systems form and evolve. The future of this field is breathtakingly bright, with more sensitive detectors like LIGO, Virgo in Italy, and Kagra in Japan continually being upgraded, and with future space-based observatories like LISA planned, we will be able to hear a wider range of cosmic events. We might detect the gravitational waves from the collapse of a single massive star, the insistent hum from the merger of supermassive black holes at the centers of galaxies, or even the faint rumble from the very birth of the universe in the Big Bang. Each signal is a direct message from the most extreme environments, telling us not just about the objects that created them, but also testing the very laws of gravity under conditions we could never replicate on Earth. We are no longer just silent observers of the cosmos. We are now listening to its deepest, most powerful rhythms. While the event horizon defines the point of no return and the singularity marks the ultimate destination, the journey of matter into a gravitational collapse is far from a quiet descent into darkness. In fact, it is often the brightest and most violent part of the entire process. This brilliance comes from the accretion disk, a swirling, superheated maelstrom of gas, dust, and stellar debris that forms as matter spirals inward, unable to fall directly in due to its own angular momentum. Think of water swirling around a drain. It doesn't just drop straight down but circles faster and faster as it gets closer to the center. In the case of a collapsing object, that drain is the black hole, and the water is matter being torn apart and heated to temperatures that defy imagination. During the total gravitational collapse of a massive star, or when a pre-existing black hole begins to feast on a companion star, this accretion process intensifies to an incredible degree. The infalling matter, compressed into a thin, frantic disk, is subjected to insane levels of friction and tidal shear. Particles rub against each other at tremendous speeds, converting their enormous gravitational potential energy into thermal energy. The result is an astrophysical oven that can heat the material to millions of degrees, causing it to glow with a ferocious intensity across the entire electromagnetic spectrum. This isn't just visible light, it's a torrent of high-energy X-rays and gamma rays, a signature of the most extreme environments in the cosmos. In many ways, we don't observe black holes directly. We observe the spectacular light show put on by their final meals in this accretion disk. The sheer luminosity of these systems is difficult to overstate. A typical accretion disk around a stellar mass black hole can outshine our Sun by a factor of 1,000 or even 1,000,000 times, all from a region not much larger than our solar system. But this is dwarfed by the disks feeding supermassive black holes at the centers of galaxies. These active galactic nuclei, or quasars, are powered by accretion disks so vast and energetic that they can outshine every single star in their host galaxy combined. The light from a quasar billions of light years away can easily drown out the light from 100 billion stars, making them among the most luminous, persistent objects in the entire universe. This incredible energy output is the direct result of matter making its final, furious plunge, converting a significant portion of its mass directly into pure energy with an efficiency far greater than nuclear fusion. For astronomers, the accretion disk is more than just a pretty light show. It's a crucial diagnostic tool. By analyzing the light emitted from different parts of the disk, scientists can map its structure and infer the properties of the invisible object at its center. The X-rays often come from the innermost, hottest region, just outside the event horizon, telling us about the extreme gravity there. The distortion of specific spectral lines, shifted and smeared by the incredible orbital speeds and gravitational redshift, allows researchers to measure the mass and spin of the black hole itself. It's like listening to the roar of a hurricane to understand the properties of the calm eye at its center. The accretion disk acts as a natural probe, illuminating the mysterious physics of the collapse zone. Furthermore, the behavior of the disk plays a fundamental role in the evolution of the black hole and its surroundings. The intense radiation and powerful magnetic fields generated within the disk can actually blow away nearby gas and dust, effectively regulating the black hole's own growth by shutting off its food supply. This feedback process is now understood to be critical in shaping entire galaxies, preventing stars from forming and explaining the observed relationship between the mass of a galaxy's central black hole and the properties of its galactic bulge. The humble accretion disk, a mere byproduct of infalling matter, becomes a cosmic engine of feedback, its intense energy influencing the fate of structures on a scale billions of times larger than itself, proving that even in the face of total gravitational collapse, creation and destruction are forever linked. Yet even as matter is devoured by the colossal gravity of a collapse, not everything is destined to fall inward. Some of the infalling material is transformed and launched back out into the cosmos with unimaginable force, creating some of the most spectacular and enduring structures in the universe. These are astrophysical jets, narrow, hypersonic beams of ionized matter and radiation that erupt from the poles of a collapsing system, often stretching for thousands or even millions of light years across intergalactic space. They are the universe's ultimate particle accelerators, and their formation is one of the most dramatic and energetic phenomena tied to total gravitational collapse. The engine for these incredible outflows is a combination of the immense gravitational energy being released and the powerful magnetic fields that are wound up to breaking point within the superheated chaos of the accretion disk. As matter spirals inward at a significant fraction of the speed of light, it doesn't just heat up, it also becomes an intensely magnetized plasma. The magnetic field lines threading through this material are stretched, twisted, and coiled by the differential rotation of the disk, much like winding up a rubber band. Eventually, this magnetic tension becomes too great, and the field lines snap, reconnecting into a new, more stable configuration. This process acts like a cosmic slingshot, funneling a fraction of the infalling material away from the disk along the path of least resistance, the rotational axis, perpendicular to the disk itself. The role of the black hole's spin and the frame-dragging effect within its ergosphere is absolutely critical in this process. A rotating black hole doesn't just drag spacetime around with it, it also helps to power and collimate these jets, focusing them into incredibly tight, narrow beams. The twisting of spacetime itself near the poles acts like a nozzle, channeling the outflow and preventing it from spreading out. This is why these jets can maintain their incredible coherence over such vast distances, unlike an explosion which would dissipate quickly. The energy extracted from the black hole's rotation, possibly through mechanisms like the Blandford-Zienagic process, provides the tremendous power needed to launch material at such fantastic speeds. And the speeds involved are truly mind-boggling. The particles within these jets are accelerated to relativistic velocities, meaning they travel at over 99% the speed of light. At these speeds, strange effects of Einstein's special relativity come into play. To us, as distant observers, the jets appear to be moving even faster than light, a purely optical illusion called superluminal motion caused by the material racing almost directly toward us. The energy contained in a single jet can be staggering, often exceeding the total output of all the stars in a galaxy for millions of years. This represents a conversion of gravitational energy into kinetic energy with an efficiency that far surpasses any power plant or explosion we could ever conceive of on Earth. We can observe the effects of these jets throughout the universe. In our own galaxy, a system like SS-433, dubbed a microquasar, is a stellar mass black hole that is actively feeding from a companion star and producing brilliant, smaller-scale jets that help us understand the physics close up. On the far grander scale, we see blazars and quasars' active galactic nuclei where supermassive black holes are feeding launching jets that are so powerful they can be detected from the other side of the observable universe. When one of these relativistic jets is pointed almost directly at Earth, we see it as a blazar, an object that fluctuates wildly in brightness across the entire electromagnetic spectrum and is a prodigious source of high-energy gamma rays. But the importance of jets extends far beyond their spectacular appearance. They play a fundamental role in the feedback processes that shape the evolution of entire galaxies and galaxy clusters. When a jet from a central supermassive black hole plows into the surrounding intergalactic gas, it heats it up and prevents it from cooling and collapsing to form new stars. This effectively regulates the growth of the galaxy itself, putting a limit on how large it can become. In the most massive galaxy clusters, jets can carve out enormous cavities, hundreds of thousands of light years across, in the hot gas that permeates the cluster. These bubbles, visible to X-ray telescopes, are a lasting testament to the explosive power of jets and their role as a cosmic thermostat, ensuring that galaxies don't grow too big too fast. This intricate dance between a destructive gravitational collapse at the center of a galaxy and the creative, regulating force of its jets is a perfect example of how the most violent events in the universe are also essential architects of its large-scale structure. But as we push our understanding to the very edge of the event horizon and peer into the heart of the singularity, we hit a wall. The equations of general relativity, which have so perfectly described the warping of space-time and the formation of black holes, suddenly spit out answers that are nonsensical infinities where there should be numbers, a complete breakdown of physical law. This isn't a failure of the mathematics. It's a glaring sign that we are missing a crucial piece of the puzzle. That piece is quantum gravity, a theory that seeks to marry the vast cosmic rules of general relativity with the tiny probabilistic rules of the quantum world. And it is in the final, unimaginable moments of total gravitational collapse, when matter is compressed to trillions of times the density of an atomic nucleus, that the effects of quantum gravity are thought to become the dominant force in the universe. At these scales, we approach the Planck density, a number so immense it defies any meaningful analogy. It is the density at which the very concepts of space and time, as we know them, are expected to break down and be replaced by something entirely new and exotic. In this realm, the classical idea of a singularity, a point of infinite density, may not be the final word. Instead, various theories of quantum gravity propose fascinating alternatives that prevent this ultimate collapse. Loop quantum gravity, for instance, suggests that spacetime itself is not smooth and continuous, but is woven from tiny, discrete loops. This granular structure would act like a quantum foam, providing a repulsive force that becomes unimaginably strong at the Planck scale. Rather than crushing down to nothingness, the collapsing matter would experience a quantum bounce, like a universe-sized spring recoiling. String theory, another leading candidate, posits that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. In this picture, the extreme conditions at the center of a collapse could lead to a transformation into a different type of exotic object, like a fuzzball, a tangled knot of strings whose surface becomes the event horizon, with no singularity at its core. These theories are not just mathematical curiosities. They offer potential solutions to some of the most vexing paradoxes in physics. The information loss problem, which arises from the classical view that information swallowed by a black hole is lost forever, might be resolved if there is no singularity to destroy that information. Instead, the information could be preserved on the surface of the event horizon or within the quantum structure of the bounce, waiting to be released. The challenge, of course, is that these are currently realms of pure theory. We cannot yet build a particle accelerator powerful enough to probe these energies, nor can we send a probe into a black hole to see what's really there. But the quest to find experimental evidence is one of the most exciting frontiers in science. Astronomers are meticulously studying the afterglow of the Big Bang, the cosmic microwave background, searching for faint imprints that could reveal the quantum nature of gravity in the universe's first moments, a period of gravitational collapse in reverse. Others are looking for subtle signatures in the gravitational waves detected by observatories like LIGO. The final chirp of a black hole merger and the way it rings down after the collision could carry within it tiny deviations from Einstein's predictions, whispers of quantum structure at the smallest scales. Perhaps the most revolutionary possibility is that we might one day create miniature black holes in particle accelerators like the Large Hadron Collider. Under certain extra-dimensional models, this could be possible at energy scales just beyond our current reach. While these tiny black holes would evaporate instantly via Hawking radiation, their brief existence and evaporation pattern could provide a treasure trove of data about quantum gravitational effects. Every new observation of the extreme universe, from the shadows of black holes to the echoes of cosmic collisions, brings us incrementally closer to hearing the quantum whisper of gravity itself, finally completing the picture of what happens when everything falls apart. But all of this, the event horizon, the photon sphere, the singularity, relies on a deeply ingrained assumption about the universe, a kind of cosmic rule that, if broken, would throw all of physics into chaos. This is the cosmic censorship hypothesis, a profound and still unproven conjecture proposed by the renowned physicist Roger Penrose. In essence, it suggests that nature possesses a fundamental modesty, a built-in mechanism that always hides the singularities formed during gravitational collapse behind the protective curtain of an event horizon. It's the universe's way of shielding us from the incomprehensible insanity of infinite density, ensuring that the predictable laws of physics we rely on remain valid everywhere outside the black hole. To understand why this censorship is so crucial, we must consider the terrifying alternative, a naked singularity. This would be a point of infinite density just hanging out in space, completely exposed to the rest of the universe without an event horizon to contain its lawless influence. According to the equations of general relativity, such an object is mathematically possible under certain extreme conditions, like if a black hole were spinning at the absolute maximum rate possible, or if it were formed from a perfectly symmetrical collapse that somehow avoided creating a horizon. A naked singularity would be a gateway to a region where the known laws of physics completely break down, where the very concepts of cause and effect become meaningless. In its presence, the predictable fabric of reality would unravel, making it impossible to calculate the future from the past. It would be a place where anything could happen, a cosmic Wild West with no rules whatsoever. The implications of discovering a naked singularity would be nothing short of revolutionary, fundamentally challenging our understanding of the universe. For one, it would force a dramatic rewrite of general relativity, or at the very least, our interpretation of it. The principle of determinism, which is the bedrock of all science, the idea that if you know the state of the universe at one time, you can calculate its state at any future time, would be thrown out the window. The unpredictable gravitational forces near a naked singularity could, in theory, create closed time-like curves, opening the door to potential time travel paradoxes and violations of causality. It would mean that events could occur without a cause, that the universe could generate information and energy from nothing, completely upending our concepts of conservation laws. Scientists have been hunting for evidence of cosmic censorship for decades, not with telescopes, but primarily through complex mathematical models and sophisticated computer simulations. They push the equations of general relativity to their breaking point, simulating the collapse of exotic forms of matter or ultra-rapidly spinning stars to see if, under any conceivable scenario, a singularity can break free of its event horizon prison. So far, every realistic simulation has shown that nature seems to find a way to preserve censorship, often through instabilities or asymmetries that trigger the formation of a horizon at the last possible moment. But the mathematical possibility remains, and this tantalizing sliver of doubt is what drives theoretical physicists to keep searching for a definitive proof or disproof of Penrose's elegant hypothesis. Ultimately, the cosmic censorship hypothesis is more than just a technical detail about black holes. It is a statement about the very nature of reality and its inherent orderliness. It reassures us that the universe, for all its violence and extremes, operates under a set of consistent, knowable rules that don't arbitrarily change from one place to another. The event horizon acts as a firewall, not for the black hole, but for us, protecting the sanctity of physics in the external universe from the unknowable chaos within. Whether this principle holds true everywhere is one of the deepest unanswered questions in fundamental physics, and its resolution will tell us if we live in a cosmos that is ultimately predictable and safe for science, or one that harbors true elemental chaos at its heart. While the cosmic scale of gravitational collapse seems forever out of reach in any laboratory, physicists have devised an ingenious way to bring a miniature version of this extreme physics right down to Earth. This happens not in a massive particle accelerator, but in a highly controlled, ultra-cold chamber where a unique state of matter known as a Bose-Einstein condensate can be made to collapse and explode in a phenomenon whimsically dubbed a Bose-nova. It's a stunning laboratory analog that allows us to watch the fundamental principles of collapse play out on a tabletop, offering a tangible window into processes that would otherwise remain purely theoretical. To understand what a Bose-nova is, we first need to grasp the bizarre nature of a Bose-Einstein condensate, or BEC. When a gas of certain atoms, like rubidium, is cooled to a fraction of a degree above absolute zero, something remarkable happens. The atoms lose their individual identities and merge into a single, coherent quantum state, essentially behaving like one giant superatom. This condensate is a macroscopic manifestation of quantum mechanics, a cloud of atoms that can be manipulated with magnetic fields and lasers. By carefully adjusting these controls, researchers can effectively create an artificial gravitational pull within the condensate itself, making it attractive to its own atoms and causing it to implode inward under its own influence. This is where the magic happens. As the condensate collapses, its density skyrockets, but it doesn't just vanish into a point. The quantum nature of the atoms fights back. A fundamental quantum mechanical principle, the Heisenberg uncertainty principle, dictates that confining a particle to a smaller and smaller space increases its momentum, creating an outward pressure that resists the collapse. In the final, frantic moments of the BC's implosion, this quantum pressure overwhelms the artificial attraction, and the condensate rebounds in a violent explosion, a tiny, controlled detonation that mimics the dynamics of a far larger cosmic catastrophe. The name Bose-nova is a perfect portmanteau, blending Bose-Einstein condensate with the word supernova, and the comparison is more than just poetic. Just as a dying star collapses under its own gravity until the immense pressure triggers a rebound explosion that blasts its outer layers into space, the BC implodes until quantum forces trigger its own miniature blast. Researchers can actually image this event, capturing the aftermath where a large fraction of the condensate is vaporized and a smaller, stable remnant is left behind, echoing the formation of a neutron star or black hole core after a supernova. By studying the size of the explosion, the amount of matter lost, and the properties of the remnant, physicists can test and refine the mathematical models that describe collapse dynamics. The true power of the Bose-nova lies in its role as a quantum simulator. The equations that govern the collapse of a Bose-Einstein condensate under artificial attraction are strikingly similar in form to those that describe the gravitational collapse of a star. The nonlinear interactions between atoms in the condensate mathematically mirror the complex feedback loops of pressure and gravity in an astrophysical setting. This means that by creating and studying hundreds of these tiny explosions in the lab, scientists can run experiments that are impossible to perform on a star. They can tweak the initial conditions, adjust the strength of the attraction, and observe the outcome in exquisite detail, all within a fraction of a second. These experiments provide crucial insights into the role of quantum effects during collapse, a factor that is incredibly difficult to model in massive astronomical objects. The Bose-nova directly demonstrates how inherent quantum pressure can halt a collapse and lead to an explosive rebound, a process that theoretical astrophysicists incorporate into their models of core collapse supernova. Furthermore, by studying how matter is ejected in the explosion, researchers can learn more about the mechanics of shock waves and the distribution of energy, which are key to understanding how supernovas seed the universe with heavy elements necessary for life. while a Bose-nova occurs at a scale billions of times smaller and under forces quintillions of times weaker than its cosmic counterparts, it serves as a powerful validation tool. It allows us to test the universal physics of collapse in a system where we have near total control, providing a crucial bridge between abstract theory and observed reality. Each tiny explosion in a vacuum chamber is a testament to the unifying principles of physics, proving that the same fundamental rules govern the behavior of a cloud of atoms a nanometer across and a star 1,000,000 times the size of our Sun. Yet, as we marvel at these laboratory-scale collapses, we return to a paradox that strikes at the very core of quantum mechanics and our understanding of reality itself. When any object, a book, a star, or an entire spaceship, plunges past the event horizon and into the singularity, what becomes of the information that described it? According to the unshakable laws of quantum mechanics, information can never be truly destroyed. It can only be scrambled or transformed. The quantum state of every particle that falls in must, in principle, be recoverable from the universe somehow. This is a foundational pillar of physics, essential for the predictability of the universe. Yet, general relativity presents us with a terrifyingly simple alternative: the singularity. This point of infinite density doesn't scramble information. It utterly annihilates it, erasing every trace of what fell in from the fabric of reality forever. This is the information paradox, and during the violent, final act of gravitational collapse, this conflict between our two most successful theories intensifies to a breaking point. For decades, the prevailing wisdom, heavily influenced by Stephen Hawking's early work, was that the information was indeed lost. Hawking argued that the radiation he predicted escaping a black hole was purely thermal, carrying no specific details about the interior content. It would be like burning a library full of unique books and claiming that the resulting heat and smoke contained no more information than the heat from burning a pile of blank paper. This Hawking radiation would be random and featureless, meaning that if a black hole eventually evaporated away, all the information about everything it had ever consumed would vanish from the universe, violating a sacred rule of quantum theory. Hawking's calculation suggested that the universe is fundamentally unpredictable, a notion that horrified many physicists and launched a quest for a resolution that has now lasted for over 40 years. The potential solutions to this paradox are as mind-bending as the problem itself. One of the most profound ideas to emerge is the holographic principle. This theory proposes that all the information about a three-dimensional volume of space, like the interior of a black hole, is actually encoded on its two-dimensional boundary, the event horizon. Imagine the event horizon as a cosmic hard drive. When an object falls in, it doesn't vanish into a singularity. Instead, its information is instantly smeared and stored across the surface area of the horizon in unimaginably tiny Planck-length pixels. The black hole then evaporates by slowly and faithfully re-radiating that information back out into the universe through subtle correlations within the Hawking radiation particles. In this view, the information was never truly lost. It was just translated into a form we are only beginning to learn how to read. The entire three-dimensional reality we perceive inside the black hole is, according to this principle, a projection of that two-dimensional data, much like a hologram that appears three-dimensional but is encoded on a flat surface. Another radical proposal is the firewall hypothesis. If information must be preserved, and if Hawking radiation does carry it away, then the event horizon cannot be the smooth, uneventful space that general relativity describes. Instead, it must be a seething, violent wall of high-energy particles, a literal firewall that would instantly incinerate anything attempting to cross it. This resolves the paradox by ensuring that information never actually enters the black hole. It is immediately converted into energy at the horizon and radiated away. However, this solution creates its own dramatic problem. It violates the core principle of general relativity, which states that an observer crossing the event horizon should experience no local, dramatic event. You can't have both the smooth spacetime of Einstein and a blazing firewall. One of the theories must break down at the threshold. This proposal is so controversial because it forces physicists to choose which cherished principle to sacrifice. Recent years have seen fascinating advancements, often driven by sophisticated mathematical tools and thought experiments. The study of quantum entanglement has become central to the debate. When a Hawking radiation particle is emitted, it is entangled with its partner that fell into the black hole. For information to be preserved, this entanglement must somehow be transferred to the new radiation particles being emitted later, a complex quantum handoff that seems to require violating the rules of how entanglement can be monogamous. This has led to proposals of intricate quantum connections between the early and late radiation. Furthermore, the application of quantum computing concepts, like the idea of black holes being the universe's ultimate quantum information scramblers, has provided new frameworks for understanding how information might be chaotically processed and eventually released. While a definitive answer remains elusive, the intense focus on this paradox is undoubtedly forcing a revolution in physics, pushing us closer than ever to a theory that can finally reconcile the quantum world with the gravitational one. But of all the energetic signatures we've discussed, none are more instantly and catastrophically brilliant than the gamma-ray burst. In the final, violent death throes of a massive star undergoing total gravitational collapse, the universe occasionally unleashes a torrent of energy so immense that it briefly outshines every star in every galaxy combined. For a few fleeting seconds, a single beam of radiation can contain more power than our Sun will output in its entire 10 billion-year lifetime. These are gamma-ray bursts, the most powerful explosions known to exist since the Big Bang itself, and they serve as the universe's ultimate flashbulb, illuminating the precise moment a star gives birth to a black hole or neutron star. The connection to gravitational collapse is direct and profound. For the long-duration bursts that can last from several seconds to several minutes, the leading model is the collapsar model. Picture a massive, rapidly spinning star many times heavier than our Sun, exhausting its nuclear fuel. Its core can no longer support its own immense weight, and it begins to catastrophically implode. In a matter of seconds, the core collapses into either a newborn black hole or a highly magnetic neutron star. But this isn't a symmetrical crunch. The star's rapid rotation flattens the infalling matter into a furious accretion disk, while immensely powerful magnetic fields, wound up by the differential rotation, channel bipolar jets of material outward along the rotational axis. These jets, moving at over 99.99% the speed of light, are the particle accelerators that generate the gamma-ray burst itself. They must punch their way out through the outer layers of the dying star, and when they finally break free, they announce their success with a pulse of high-energy radiation that can be seen across the cosmos. We are not merely theorizing about this chain of events. We have observed the smoking gun. Space telescopes like NASA and Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope are our sentinels, constantly scanning the skies for these sudden flashes of gamma rays. When Swift detects a burst, it automatically and rapidly slews to point its X-ray and ultraviolet/optical telescopes at the location, capturing the rapidly fading afterglow. It is in this afterglow that astronomers have, on multiple occasions, detected the unmistakable spectroscopic signature of a supernova, a massive star exploding. This critical observation solidifies the link. A long gamma-ray burst is not just associated with a supernova, it is the supernova, or more precisely, it is the spectacular birth cry of the compact object, the black hole or magnetar formed at the heart of that supernova. The gamma-ray burst is the directed beam from the stellar engine, while the supernova is the spherical explosion of the star's outer envelope. This makes gamma-ray bursts incredible natural laboratories for studying the physics of gravitational collapse under the most extreme conditions. The properties of the burst itself, its duration, its energy spectrum, how its brightness flickers encode detailed information about the central engine. The rapid variability in the light curve, for instance, tells us about the timescales of processes happening near the black hole, likely related to instabilities in the inner accretion disk. The total energy output allows us to estimate the efficiency of this cosmic engine at converting gravitational mass into pure energy and accelerating particles. By studying the afterglow across different wavelengths, we can deduce the geometry of the jet, the density of the surrounding environment, and the magnetic field strength, painting a comprehensive picture of the aftermath of collapse. Furthermore, because gamma-ray bursts are so phenomenally luminous, they act as cosmic lighthouses, visible from the very edge of the observable universe. The most distant bursts we have detected originated when the universe was less than 1 billion years old, a mere fraction of its current age. This allows astronomers to use them as probes to study the early cosmos. The gamma rays from these ancient events travel for billions of years across expanding space, and their light is subtly altered by the tenuous fog of interstellar and intergalactic material it passes through. By analyzing the absorption lines in the afterglow spectrum, scientists can take a census of the elements present in these early galaxies and measure how the universe was reionized after its dark ages. Each burst is a fleeting message in a bottle from the universe's youth, carrying with it information about the first generations of stars and their spectacular, collapse-driven deaths. But the universe offers a spectacular alternative to the silent darkness of a black hole. When a massive star collapses, its fate is not always sealed as an eternal prison for light. Under the right conditions, this catastrophic implosion can be halted at the last possible second, resulting in one of the most bizarre and wondrous objects in the cosmos, a neutron star. This is the universe's ultimate act of compression, where the very protons and electrons of atomic nuclei are crushed together, forced to merge into a solid ball of neutrons. Imagine taking the entire mass of our Sun, a sphere over 860,000 miles across, and squeezing it down into a city-sized object no wider than Manhattan. The density achieved is so incomprehensible that a single sugar cube-sized piece of this material would weigh as much as a mountain, over 1 billion tons on Earth. This miraculous halt to total collapse is thanks to a quantum mechanical force known as neutron degeneracy pressure. When matter is compressed beyond a certain point, the fundamental rules of quantum mechanics forbid subatomic particles from occupying the same state, creating a powerful repulsive force. For a collapsing stellar core, this pressure acts as a final, immovable barrier against gravity's relentless crush. But this battle is not won easily. The core of the star, which may have started out larger than our Sun, rebounds from the point of maximum compression. This rebound sends a tremendous shockwave blasting outward through the infalling layers of the star, tearing it apart in a spectacular supernova explosion that can outshine an entire galaxy. Meanwhile, the core survives, left behind as an ultra-dense remnant, a newborn neutron star. The birth of a neutron star is an event of unimaginable energy release, but much of that energy is not in the form of light. For every single atom that makes up the star, about 10 billion ghostly particles called neutrinos are produced in the chaotic first second of formation. These neutrinos, which interact with matter only through the weak nuclear force, flood out from the core, carrying with them 99% of the supernova's total energy. This neutrino burst is not just a byproduct, it plays a crucial role in the very mechanics of the explosion. As these countless neutrinos stream outward, they deposit some of their energy into the stalled shock wave, helping to power it through the dense outer layers of the star and ensuring the supernova completes its violent rebirth. Detectors here on Earth, like Super Kamiok and in Japan, have actually captured these neutrino pulses from supernova in other galaxies, providing direct confirmation of this incredible particle-driven process. What remains after the cataclysm is a cosmic laboratory of extreme physics. A neutron star's surface gravity is about 200 billion times stronger than Earth's, and its magnetic field can be a quadrillion times more powerful than our planet's protective magnetosphere. These properties give rise to some of the most observable and useful phenomena in astronomy. If a neutron star is spinning rapidly and its magnetic poles are misaligned, it becomes a pulsar. Like a cosmic lighthouse, beams of radiation from its poles sweep across space with metronomic precision. The timing of these pulses is so incredibly regular that it rivals atomic clocks, allowing astronomers to use them as celestial navigation beacons to study the fabric of spacetime itself, and even to detect the faint ripples of gravitational waves. Then there are the magnetars, a special class of neutron stars with magnetic fields so intense they verge on the unbelievable. The magnetic field of a magnetar is so powerful that it could strip the information from every credit card on Earth from halfway across the solar system. These fields are under immense stress, and when they suddenly snap and reconfigure, an event called a starquake, the magnetar releases a flare of gamma rays and X-rays more energetic than anything our sun could produce in 100,000 years. These outbursts serve as stark reminders of the titanic forces locked within these tiny, spinning orbs, and they provide a unique window into the behavior of matter and magnetism under conditions we can never hope to replicate on Earth. By studying neutron stars, we are probing the absolute limits of material strength and nuclear physics. They represent a state of matter that cannot exist anywhere else. A superfluid, superconducting core that may contain exotic particles like hyperons or even free quarks. The maximum mass a neutron star can support before it collapses further into a black hole tells us fundamental properties about the strong nuclear force that holds atomic nuclei together. Each new pulsar discovered, each gamma ray flare from a magnetar, and every gravitational wave signal from a colliding neutron star pair provides another critical data point. These celestial remnants are not just the end products of stellar death. They are Rosetta Stones, helping us translate the laws of physics that govern the most extreme environments in the universe, teaching us what matter itself is ultimately capable of. But what if the story of total gravitational collapse doesn't have to end with a one-way trip into darkness and a singularity? What if there's a theoretical back door, a cosmic emergency exit that turns the entire process on its head? This brings us to one of the most speculative and fascinating ideas in all of theoretical physics, the white hole. Imagine a black hole in reverse. Instead of an event horizon that acts as a point of no return, sucking everything in, a white hole would possess a horizon that is a point of no entrance, violently expelling all matter and energy outward. Nothing could ever cross into a white hole. It would be like a cosmic fountain, endlessly spewing material into the universe from its mysterious interior. While there is not a single shred of observational evidence that white holes exist, they emerge as valid, if exotic, mathematical solutions to Einstein's field equations of general relativity, presenting a stunningly alternative outcome to gravitational collapse. The concept of a white hole is intrinsically linked to the idea of time reversal. The laws of physics, particularly on a large scale, are mostly time-symmetric. If you were to take a film of a planet orbiting a star and play it backward, it would still look perfectly physically plausible. Apply that same logic to a black hole. If you reverse the flow of time in the equations describing a black hole's formation and behavior, you get a white hole. A black hole is formed by matter collapsing inward past an event horizon. Its time-reversed counterpart would be an object that began its existence with matter exploding outward from a horizon. In this speculative picture, the total gravitational collapse of a star might not be the end, but a transition, a bounce. Instead of forming a permanent black hole, the collapsing matter would reach a point of maximum density and then rebound, exploding back out as a white hole. This quantum bounce idea, suggested by some approaches to quantum gravity, offers a tantalizing alternative to the frightening finality of the classical singularity. White holes also appear in another captivating theoretical construct, the Einstein-Rosen bridge, more commonly known as a wormhole. In this classic solution, a black hole and a white hole could be connected by a tunnel through space-time, a shortcut between two distant points or even two different universes. The black hole would be the entrance, the irresistible gravitational drain, while the white hole would be the exit, the place where all that captured matter and energy is vomited out elsewhere in space and time. While this provides a mathematically elegant way to avoid the information paradox, information isn't destroyed, it's just relocated. It comes with its own set of massive problems. These wormholes are predicted to be incredibly unstable, pinching off into nothingness in a fraction of a second before anything could ever hope to travel through them. Furthermore, the white hole end of the bridge would be violently explosive, making it a decidedly unfriendly destination. The existence of white holes would fundamentally challenge our understanding of cosmic evolution and the second law of thermodynamics, which states that entropy or disorder always increases. A white hole spontaneously appearing and spewing out ordered, low-entropy matter seems to violate this core principle by effectively decreasing entropy in its local environment. Physicists have argued that this makes white holes thermodynamically forbidden, effectively impossible within our universe's arrow of time. They represent a region of space-time that is, in a sense, younger than the universe around it, having not shared in the universal increase in entropy since the Big Bang. This is perhaps the strongest argument against their natural existence. They seem to demand a reversal of time's arrow that is inconsistent with the universe we observe. Despite these formidable obstacles, the concept of white holes continues to captivate cosmologists because it forces us to ask deeper questions about the nature of space-time and the initial conditions of the universe. Some have even proposed a radical idea that the Big Bang itself was a white hole event, the ultimate white hole, from which all the matter and energy of our entire cosmos erupted. This perspective reframes the beginning of everything not as a singularity in the past, but as the explosive output of a white hole originating from a parent universe, part of a vast cosmic cycle of collapses and rebirths. While firmly in the realm of speculation, this kind of thinking demonstrates the power of the white hole concept to stretch our imaginations and challenge the most foundational stories we tell about the cosmos, pushing us to consider that the ultimate fate of a gravitational collapse might not be an end, but a spectacular new beginning in a place we cannot yet see. The incredible warping of spacetime around a gravitational collapse doesn't just trap light or slow time. It can also act as the most powerful magnifying glass in the universe, a natural telescope of unimaginable scale. This phenomenon is known as gravitational lensing, and when it occurs near the extreme densities of a black hole or neutron star, its effects are amplified to breathtaking levels. According to Einstein's general theory of relativity, mass tells spacetime how to curve, and that curvature tells light how to move. When light from a distant star, galaxy, or quasar passes close to a massive, collapsed object on its journey to Earth, its path is bent and distorted by this curvature. The result is a cosmic illusion, a trick of gravity that can magnify, multiply, or twist the image of the background source into beautiful and intricate patterns, including perfect rings of light known as Einstein rings. These patterns are far more than just pretty pictures. They are precise scientific instruments. The specific way the light is bent depends directly on the mass of the object doing the bending. For a black hole or neutron star, this provides one of the most accurate methods we have to measure its weight. By carefully analyzing the distortion the size of an Einstein ring, the separation between multiple images of the same galaxy, or the length of a luminous arc, astronomers can perform a gravitational audit, calculating the mass of the invisible collapsed object with incredible precision. This is how we can confidently state the mass of the supermassive black hole at the center of a distant galaxy, even though we cannot see the black hole itself. The light from objects behind it is twisted into a map that charts the intensity and shape of its gravitational field, revealing its hidden properties. The most striking manifestation of this is the Einstein ring, a near-perfect circle of light that forms when a distant light source, the massive lensing object, and our telescope are in almost perfect alignment. It's a rare and beautiful symmetry that occurs when the gravity of the foreground object bends the light from the background source evenly in all directions, creating a halo. While smaller objects like stars or galaxies can create these rings, the effect is dramatically amplified and more stable when the lens is an ultra-dense remnant of gravitational collapse. The sharp, clean rings produced by these objects provide the clearest possible data for scientists to decode, offering a direct window into the geometry of spacetime in these extreme regions. With the advent of powerful new observatories like the James Webb Space Telescope, our ability to use this natural cosmic telescope has been revolutionized. Webb's incredible sensitivity and resolution in infrared light allow it to see through cosmic dust and detect lensed galaxies that are among the most distant and ancient ever observed. These early galaxies would normally be far too faint to see, but the gravitational amplification provided by a foreground cluster or black hole can magnify their light by factors of 10, 20, or even more, bringing them into clear view. This allows us to study the formation of the very first stars and galaxies in the universe, using the gravitational collapse of later objects as a natural lens to peer back into the deepest past. Beyond just weighing black holes and magnifying distant galaxies, strong gravitational lensing is now being used to probe the very nature of the dark matter that surrounds these collapsed objects. Most of the mass in a galaxy cluster, which acts as a powerful lens, is invisible dark matter. By mapping how the light from background galaxies is distorted by the cluster's gravity, astronomers can create a detailed map of where the mass, including the dark matter, is actually located. This has revealed that dark matter forms a smooth, pervasive halo around galaxies and clusters, and its distribution appears to be influenced by the presence and mergers of supermassive black holes at their centers. Looking to the future as our telescopes become even more powerful and our analysis techniques more sophisticated, gravitational lensing may reveal even more exotic insights. Could subtle flickers or anomalies in an Einstein ring betray the presence of smaller, orbiting black holes or dense planets around a central massive object? Might we detect the lensing signature of a solitary, rogue black hole drifting silently through interstellar space, completely dark except for the way it distorts the stars behind it? Each distorted image and every ring of light is a complex puzzle, a snapshot of gravity's power that allows us to study the invisible architecture of the universe and understand the final, dramatic moments of a star's life long after the collapse itself has faded from view. Even the very void of space itself is not immune to the transformative power of a gravitational collapse. We often think of a vacuum as pure nothingness, an empty stage upon which particles perform. But quantum mechanics reveals a far more fascinating and dynamic reality. At the tiniest scales, even in the deepest void, the vacuum is a seething, bubbling sea of activity. Particle-antiparticle pairs constantly flicker into existence, borrowing energy from the universe for an immeasurably brief moment before annihilating each other and vanishing back into the nothingness from which they came. This is the quantum foam, the fundamental fizz of empty space. Now, place this quantum frenzy near the immense gravitational field of a collapsing star or black hole. The sheer force of that gravity distorts this delicate quantum activity, polarizing the vacuum and turning empty space into an active participant in the physics of the collapse, a phenomenon known as vacuum polarization. This isn't just a theoretical abstraction, it has direct, observable consequences. In fact, vacuum polarization is the very engine behind one of the most famous phenomena we've discussed, Hawking radiation. Remember those virtual particle pairs popping in and out of existence near the event horizon? The intense gravitational gradient provides the energy needed to make one of those particles real, permanently separating it from its partner. The particle that falls in has negative energy, which effectively reduces the mass of the black hole, while its partner escapes as genuine radiation. This entire process is driven by the polarization of the quantum vacuum by the black hole's gravity. It's a stunning example of how the nothingness of space, when twisted by immense gravity, can become a source of something tangible, slowly evaporating the most powerful gravitational trap in the universe. The implications of this go far beyond just Hawking radiation. This polarization effect means that the event horizon, the point of no return, might not be the clean, mathematical boundary that classical general relativity describes. The quantum vacuum's altered behavior could potentially influence the horizon's stability and its very definition on the smallest scales. Some theories suggest that at the Planck scale, the horizon might be a chaotic, frothy region due to these extreme quantum fluctuations, blurring the sharp line we imagine. This challenges the classical picture and suggests that the interface between the black hole and the rest of the universe is a far more complex and dynamic quantum system than we once believed. Studying vacuum polarization in these extreme environments is a critical step in our quest to unify gravity with quantum mechanics. It forces us to apply the rules of quantum field theory, which usually operates on the flat, static spacetime of special relativity, to the wildly curved and dynamic spacetime of a gravitational collapse. This is the realm of quantum field theory in curved spacetime, a sophisticated framework that allows physicists to calculate how quantum fields behave when the very stage they perform on is warped and moving. It's a crucial halfway house on the road to a full theory of quantum gravity, providing valuable insights without requiring all the answers first. So, how does this alter our perception of empty space near a singularity? It completely revolutionizes it. We can no longer think of the space surrounding a black hole as a passive, empty volume. Instead, it is a roiling, active medium, polarized and animated by the immense gravitational forces at work. That nothingness is teeming with quantum potential, a cauldron of virtual particles being ripped apart and made real. This means that the journey toward a singularity isn't through a featureless void, but through a space that is itself alive with quantum activity, a final, frenetic dance of energy and information at the edge of oblivion. It suggests that even in the face of infinite density, the quantum nature of reality asserts itself, ensuring that true nothingness may not exist anywhere in the cosmos. And so we arrive at a concept so profound it seems to bend the very nature of reality itself, suggesting that everything we perceive about the universe might be a magnificent illusion. This is the holographic principle, a radical idea born from the fiery intersection of black hole thermodynamics and string theory. It proposes that during a gravitational collapse, all the information that described the star, the planets it might have swallowed, or even an entire spaceship that fell in, every last bit of data that seemingly vanished into the singularity, is not destroyed. Instead, it is meticulously encoded onto the two-dimensional surface of the event horizon, the black hole's boundary. The three-dimensional world we experience, with its rich depth and volume, might be nothing more than a projection, a cosmic hologram emanating from this flat, information-rich surface. This astonishing idea emerged from a desperate attempt to solve the information paradox. Physicists asking what happens to information led them to calculate the entropy of a black hole, a measure of its information content. They found it wasn't proportional to the black hole's volume, as one might expect, but to the surface area of its event horizon. This was a monumental clue. In everyday systems, entropy scales with volume. A larger box can hold more disordered air molecules than a small one, but for the most extreme gravitational objects, the maximum possible information content is defined by their surface area. It's as if a three-dimensional object is somehow constrained by the limits of its two-dimensional skin, suggesting that the skin is where the real information is stored. The holographic principle takes this clue and runs with it, proposing that this isn't just a weird black hole quirk, but a fundamental property of the universe. To grasp this, imagine the event horizon as the universe's ultimate pixelated display. Each Planck-sized area, the smallest possible unit of space on the horizon, is thought to hold roughly 1 bit of information. The entire history and composition of everything that ever fell into the black hole is scrambled and stored across this vast, ultra-high-resolution screen. The black hole itself, with its seemingly deep interior, would then be a projection of that data, a three-dimensional interpretation of a two-dimensional reality. This isn't just a metaphor. The mathematics of string theory provides a concrete, working example of this principle in action, showing how a gravitational theory in a higher dimensional space can be perfectly equivalent to a quantum field theory operating on its lower dimensional boundary. If this principle is true, it would provide an elegant and powerful resolution to the information paradox that has haunted physics for decades. Information isn't lost in the singularity because it never actually travels into a three-dimensional interior to be destroyed. It is translated and imprinted onto the event horizon at the moment of crossing. Then, as the black hole slowly evaporates through Hawking radiation, that information is not carried away by random thermal noise. Instead, the subtle quantum correlations between the radiated particles act like a slow, meticulous transmission, faithfully broadcasting the encoded information back out into the universe. The black hole behaves less like an incinerator and more like a colossal hard drive that eventually reformats itself, ensuring the cosmic ledger of information remains balanced. The implications of this stretch far beyond black holes, potentially rewriting our understanding of the entire cosmos. The holographic principle suggests that our entire universe, with its three spatial dimensions, might itself be a holographic projection from a two-dimensional surface at the very edge of the observable universe, on a scale we cannot yet comprehend. The laws of physics that we experience, including gravity itself, may emerge from a complex quantum interaction happening on this distant boundary. This would mean that gravity is not a fundamental force, but a secondary effect that arises from the way information is organized and processed on this lower dimensional surface. It's a concept that turns reality inside out, proposing that the deepest truths about our universe are not found by looking inward into space, but by understanding the constraints of the surface that contains it. This principle offers a potential pathway to finally reconciling Einstein's theory of gravity with the quantum world. The major obstacle to a theory of quantum gravity has been describing the fluctuating, granular nature of spacetime at the tiniest scales using the smooth, continuous language of general relativity. The holographic principle sidesteps this problem entirely. It suggests that we don't need to quantize gravity in a three-dimensional world because gravity in three dimensions is actually a manifestation of a well-understood quantum theory without gravity operating in two dimensions. We already have the tools to describe that quantum world. The challenge is in decoding the translation manual that turns those two-dimensional quantum processes into the three-dimensional gravitational reality we inhabit. This could be the key that unlocks the final, unified theory of physics, revealing a universe that is, at its heart, a vast and unimaginably complex computation of information.